Hi, my name is Ryan Booz. I'm a solutions engineer here at pganalyze, and today I'd like to begin episode 4 of our deep dive series into pgstat statements. And this episode is honestly really exciting to me because we're going to go look at the source code and the workflow of exactly what happens inside of pgstat statements. And because of that, I will warn you up front that this episode will be just a little bit longer than the others in this series. Now, as with anything in Postgres, we can go look at the source code. That's the beauty of an open source database. And when it comes to pgstat statements, I actually had to do a deeper dive into this about a year ago. I had some questions about some of our customers and why their deallocation counter was going up so quickly and why some of their metrics seem to be missing. I've been using Postgres for a long time, and I've relied on pgstat statements often to try and find those queries and those statements that were possibly those problematic queries. During that conversation of why those counters are going up, someone said, hey, let's go look at the source code and try and get that understanding for this specific problem. And I will say that as I began to look through this, I gained a better appreciation for exactly what's happening. Now, as you look through the source code, you'll start to see things we've already discussed. Things like that key for the hash table itself, user ID and database ID, the query ID, and that top level Boolean of whether or not this is the top level query or something that was executed inside of a function. You'll also see that the statement, the values that come out of pgstat statements info view, that deallocation counter that we've talked about so often, and really the focus of trying to understand how pgstat statements works in saving this information. And then we have the pgstat statements entry struct. Now, this is the structure of the data essentially that we get to see in the view, or at least most of it. That information is stored in the counters value here within this structure. It's essentially an array of the data for each query. The number of calls and the total time and the mean time and JIT and buffers read, all of those things are stored here in this counters array. And then in the last episode, we talked about that external file, and you'll see that we have those values stored here, the offset in that file where the beginning of this query text is and how long the query text is in that file. And then finally, we have the shared state structure. And this has a number of variables that are necessary for pgstat statements to work across processes. But one of the things that's really essential to one of the processes we're going to look at today is that mean query length variable. And so we'll see that in just a minute and exactly why that's so important to understand. Now, as I've looked at the code more and more through this last year, I've really come to appreciate the fact that pgstat statements will do everything possible to retain the information that is incoming. When that query finishes executing, those metrics will be stored to the best of its ability. It might mean that you're losing some historical data, and we've talked about that over and over again already in the series. When you have a deallocation counter going up, it means there are metrics that have been removed. And if your monitoring software or the way that you're monitoring pgstat statements isn't keeping up appropriately, you might have missing information about what's going on in your application or your database. As I've looked at the code, I've come up with 3 things that I think are really necessary to understand about the process. Now, there is more to this. There's a lot more in here. These are just the 3 things that I want to make sure that you understand a little bit better, particularly around deallocation. Now, one is pgstat statements max, for sure. The other one is this value called usage, which is actually a metric that's stored inside of that counters array value that we talked about. We just never see it. It is not returned in the pgstat statements view, but it's used to help determine which statements get deallocated. And then that mean query length that we mentioned just a few minutes ago, we'll see how that works too. So we've talked about pgstat statements.max quite a lot so far in the series, and it works just as we've said. When a new entry comes in and that query has not been stored before, or at least it is not currently in the hash table, if the total entries equals that max setting, then pgstat statements has no other path. The very first thing it has to do is deallocate some space, make room for this new entry coming in, and possibly trigger a truncation of that file externally to shrink it down a little bit because it's gotten too big. And then we have that usage value that I just mentioned. This is, as I said, a per query counter that is stored alongside all the other metrics. It is incremented at a +1 value every time a query finishes executing. Now, the interesting thing is that it is actually increased by this function called usage exec, and it passes in total time. But you'll notice up there that it is actually then statically typed to a value of 1. And so every time it's called, it does pass in total time, but it's not adding up total time. It's just incrementing this usage value by 1. It's really interesting that there is still a note here that says, hey, is this the right approach? Should we be using time or maybe buffer usage to better reflect which queries are most used, the ones we want to keep around the longest? It's just an interesting thing to recognize that this discussion has been ongoing. Now, that also means an interesting fact. When the pgstat statement starts empty, until a deallocation occurs, until that first deallocation, calls and usage will essentially be the same number because they're going up by 1. But as soon as max is reached and a deallocation has to occur, then all of the usage values get decreased by 1%, or I should say most of the values. You'll see why in just a minute. And then it sorts all of the values and it drops the lowest 5%. So that's how that usage metric is used. And then we have mean query length. This is the mean length of all the texts currently in the hash table, and it's actually only updated when deallocation occurs. During the deallocation process, right before that bottom 5% is dropped, pgstat statements finds the mean of the current query lengths in the table, and that value is used to help determine if the external file is more than twice the expected length. And if it is, then it has to be shrunk as well. Now, before we move on, I want to make sure we are on the same page about one thing, and that is that pgstat statements only stores metrics for completed executions. It is called during the executor end hook, after planning and after all the other things are done. That means that no aborted or timed out metrics are actually stored in the values that we see. If you have a statement timeout set to 30 seconds and a query runs for 30 seconds and reads hundreds of thousands of buffers, those values are not shown in pgstat statements. They're not stored there. Only completed execution metrics are stored. It does not matter what your current AI says. We queried this in May of 2026 when I'm recording this video, and I can tell you this is 100% wrong. There is nothing in the code that you will see in pgstat statements that stores metrics for timed out queries. It's not true. And that is actually one of the problems the community continues to deal with right now. How do we get a better understanding of how many times one of these statements is timing out and how much work was done during that period before it timed out? Right now, we don't know. And so that's something we just need to be aware of as we're looking at all these metrics. Now, as we go to talk about the actual code itself, I thought it was interesting just to realize when you take out the comments, this is not a very big process. It's only about 1,800 lines of code. A lot of it is defense against making sure we're storing the right things at the right times. Now, in my reading of this code, I see essentially 3 primary functions about storing data. There are a lot of other functions in here for specific purposes, but we are primarily concerned about 3 of them. Those are the pgss store function. That is, every single completed execution goes through this function to start storing the values. And then whether or not it just updates values or allocates entries happens through the other functions. If the data that's coming in is for a statement that does not yet exist, it needs to go through the entry alloc function. And then during allocating a new entry, if we determine that pgstat statement's max has been reached, then we have to go through the entry dealloc function. And then there are 2 other, what I consider secondary functions that are really geared towards managing that query text file, which is really important to maintaining pgstat statements. The first is needs garbage collection, essentially is what that means. And that just simply determines, hey, is that external file too large so that later in this workflow, we're going to truncate it and free it up? If the answer to that is true, then we actually at some point will call the garbage collection function, which will rewrite that file with the then current query texts that are now in the deallocated or shrunken pgstat statements hash table. Now, the overall workflow is honestly pretty simple. Although there's a lot of complexity in how it works, this is a really quick overview. As we said, primarily we begin this process at the end of an execution. We go through pgstat store, it looks up the hash. If it exists, it simply updates the counters and we're done. It's really fast, it's all shared locks, and we can move on. If that entry is not found, then we go through another process. First, hey, is the table full? Have we reached pgstat max? If the answer is no, we still take an exclusive lock, which I tried to show here in red, but it's a little bit easier. We allocate a new entry, we make sure the query text gets put in that file, we update the metrics, and we move on. The tricky part does come in that deallocation phase. If the table is full, now we have to deallocate, we may have to truncate the text file, then we still have to allocate a new entry because we freed up space, and then update the metrics and so forth. So you can see that if the table's full or you are churning through a lot of statements and often deallocating, this becomes a much longer process and you're doing it in a state of exclusive lock more often. So at a more clear view, or more close view I should say, this is what the pgstat store does when the value is found. We simply look it up, we find it in the hash table, take this shared lock, update the counters, and release all locks. That is the best path forward. And if you are kind of in a maintenance state of a constant workflow, hopefully this is mostly what's happening in your database. Now, the most complex workflow is when we don't find that entry. There's a lot of work that has to be done. And so taking a closer look at it, we go through pgstat store, find that we don't have that entry, and so we then switch from a shared lock to an exclusive lock. And we go ahead and make sure that text file has been updated and see if later on we're going to have to deallocate or shrink the text file. And then we start to check some of the things we've talked about. Have we hit pgstat max? If the answer is yes, we're going to deallocate. And that means we have to go through the deallocation phase. We keep that exclusive lock, it's currently held. We decrease all the usage by either 1% or 50% if it's a sticky entry. We then sort all the values and remove the bottom 5%. It is at that point that we increment the deallocation counter, and then we still have to go back and save the data that came in, which triggered this process. Now, one thing I want to point out here is that if you have a high value for max, let's say you've updated your max value to 10 or 50 or 100,000, that means you have to sort and modify the usage values of 100,000 rows every time deallocation occurs. So it is something that you need to be aware of. It is a linear process. If you simply allocate more space to pgstat statements, you are going to pay the cost at some other time and potentially create more opportunity for locking. There is a little bit of dance that does occur here with configuring pgstat statements well. This is the code that does exactly what we just said within pgstat statements, the deallocation section. We read in the actual current hash table, we decrease those values, we sort them, we find the ones that are the lowest of the number that we've determined we need to drop, we free them up, and then we increment the counter. And that's it. That's how it works. This is all happening in an exclusive lock, but it's pretty straightforward in how this occurs. And then once deallocation has occurred, we can finally go back to that entry allocation. Now, whether or not we actually went through deallocation, eventually we're going to end up at the entry allocation phase of this process. And when we get to this phase, whether we deallocated or not, the first thing it does is search one more time for the query it's about to allocate. And you might think, well, why does it do that? We obviously got through this path because the entry didn't exist. Well, there are other processes that are running queries. And so during this little switch between locks and maybe deallocating, there's a chance that another process got this same query from another call and was able to store a reference to this query in the hash table. And so we just check one more time to make sure we are the ones that are going to allocate it. And then right before we allocate, we actually check to see, hey, remember, did that needs garbage collection come back as true? Was it 2 times pgstat statement max times that mean query length that we talked about earlier? If it is, what happens is we load the text file into buffer. We essentially load the entire thing in, and so you will need that much memory to actually do this. And then we go ahead and allocate that file again. So we're actually reading the file in an exclusive lock, and then we are overwriting the file in place. We are not writing a new file with a delete copy. We are overwriting the file that is actually there. Now that we have all of those statements in memory, we are searching through the new hash table and writing out the queries that are necessary to be written to that file. And then at the end of that, we actually just say, hey, this is the end of the file now. You can truncate off the end. It's a C function that works really quickly. And once that's done, then we can go ahead and allocate that entry, initialize the counters for this new entry, and then we're done. And so you can see there's a lot at play here with pgstat statements. The simplified workflow looks pretty simple until you get into this contentious piece where you might have more information than pgstat statements is able to maintain. And so in the last couple episodes, we're going to talk about some of the configuration that really matters, things you can choose to turn on or off, which can help. We've already talked about some things like Postgres 18 helping with those where in clauses to reduce the number of unique normalized queries. And then we'll look at a few other things quickly over the last two episodes. What does it really look like in high cardinality workloads? And then in episode 7, we're going to look at some ways that you can safely use pgstat statements to most effectively manage your query workload. So I hope you'll come back and finish out the series with me, and you've enjoyed getting a look at the source code and the workflow of pgstat statements. We'll see you soon.